So we have a building, which is a structure that stands alone or that is cut off from adjoining structures by firewalls with all openings therein protected by approved fire doors. So, a building is a standalone structure or a structure separated by firewalls. You might get into an issue where a ground mounted solar array considered to be on a building or not. If this is on a building, you have to do rapid shutdown. Well, I think it's smart on ground mounts to do rapid shutdown combiner boxes. It depends on where you locate the equipment. If the inverter is mounted on the building wall, that's considered to be on a building. Maybe your local jurisdiction will let that slide, maybe they won't. What's the difference between a building and a garage? A garage is a portion of a building where vehicles are kept. So a garage is still considered to be a building, and it's not exempt from code simply because it's a garage. It's just that there may be different code requirements for dwelling units rather than garages that don't have any dwelling that goes on inside them unless they're attached to a dwelling unit. Bonding, connected to establish electrical continuity and conductivity. So the question is, well, what's the difference between bonding and grounding? And the answer is there is not much difference. Bonding is concurrent flow between two things, and all of your metal parts are bonded together, and all of your metal parts are attached to that equipment grounding conductor. So, whether or not you say the metal is bonded to the equipment ground conductor or the all metal parts are grounded, I guess saying that the metal is bonded to the equipment ground conductor is more specific than just saying all the equipment is grounded. All of the metal parts on your systems must be bonded together. Now there's different requirements for when you're under 250 volts and over 250 volts. But, basically when we're talking about solar power and on-site energy management systems, you need to ground all metal parts, and you'll make mistakes when metal parts that you think don't need to be grounded do actually need to be grounded. All your metal parts and your battery systems, etc., need to be grounded. And so you might have your solar rail that is metal, and your modules are connected to your solar rail, but that doesn't necessarily mean they have the electrical connectivity. They need to conduct electricity, and metal has, whenever it has like an anodized finish on it, that instead of being a raw piece of metal, they coat it, and they coat it for corrosion resistance, they coat it for aesthetic purposes, and that coating eliminates the conductivity. And so you have to have, what we see down in the middle lower picture is a grounding washer between two pieces of rail. Now there's a stick of metal, right smack dab in the middle of these two pieces of rail, and that piece of metal is there to splice the rails together and turn them into one rigid piece of rail instead of two separate pieces of rail. But that splice is not listed as a ground path. And so here we have a separate bonding jumper that bonds the two pieces of rail together. And so that's another thing, is just because it's metal touching metal, that doesn't mean that it's actually qualifies as a ground path. Piles that are driven directly into the ground. You think, well, the ground is the ground, and that's metal going into the ground, but it may not have enough resistance to qualify as a ground path. Two pieces of anodized metal racking being pressed together does not qualify as a ground path. An enclosed assemblage of equipment, switches, circuit breakers, buses, and transformers under the control of qualified persons through which electric energy is passed for the purpose of switching or modifying its characteristics. Substations will take your high voltage lines that are coming from the power plant and then convert that into medium voltage that'll go out to your communities. And then there'll be another medium voltage conversion that'll step it down to your distribution circuits, and then another transformer conversion that steps it down to your power lines that come into your home, which are your 240 volt split phase or 208 three phase or 208 delta, 208Y. Then we get into table 225.3, which is the table of contents of the National Electric Code that tells you, there's all these other special rules for branch circuits, special rules for communication, fire alarm systems, de-icing and snow melt systems, all of these, boat docks. You want to design a floating solar array. Well, there's a section of National Electric Code out there that governs floating buildings. So a new definition, raceway, an enclosed channel of metal or non-metallic materials designed expressly for holding wires, cables, or bus bars with additional functions as permitted in this code. And the key word here in raceway is enclosed. And the definition of enclosed is surrounded by a case, housing, fence, or wall that prevents persons from accidentally contacting energized parts. And so the issue is, you might have let's say you want to do building integrated solar, where you have a house, and rather than putting the modules onto the rooftop, you actually want to make the roof out of the solar modules themselves. And so you're building your rafters, and let's say you do some glass on glass solar modules. And so you have glass on glass solar modules, and that's pretty nice because that's nice and well insulated, as far as the interior of your building. But so here's your rafters, and you're putting down your glass on glass modules, and you're using like butyl skyscraper glue to seal the glass together. And that's something that, more of a building framer will be better suited to do. So here's your rafter, here's your solar panel, and building integrated solar you can do with the existing products that are out there on the market. But the problem with building integrated solar is more that now you have these cables coming off the underside of the module. And what we'll see a bit later is direct current circuits must be in an enclosed metal raceway. And so the question is, if you have these exposed circuit conductors that are not fully enclosed in a metal raceway, then you're just asking for a code violation. If you have DC conductors coming off the back of the module and they're inside the home, they must be in a metal raceway. But if they're not in that metal raceway, then how do we enclose them in a metal raceway? You might get a nitpicky inspector that would fail you unless you identify that, hey, we're going into the metal raceway as soon as we can in this system, but that might mean there might be a half an inch of space. And so you want to point this stuff out during the design process to the AHJ so that you can do fancy building integrated solar projects. Ground fault, an unintentional electrical conducting connection between an ungrounded conductor of an electrical circuit and the normally non-current carrying conductors of metallic enclosures, metallic raceways, metallic equipment, or earth. In other words, whenever you have an ungrounded conductor, that's a conductor at high voltage, and then it connects to that non-current carrying metal conductor, and it faults and that current connects to ground. And that might sound like, oh no, there's something wrong, and there is. You know, a ground fault that is not planned for nor expected is not a good thing. But what would be worse is for that ground fault not to occur and for that metal box or that metal conduit on the building to be energized, and you go up and touch it and you become the ground path, and that's even worse. You know, when we do have ground faults, we need to have a path to ground for that ground fault to carry over. And then we have the ground fault circuit interrupter, a device intended for the protection of personnel that functions to de-energize a circuit or a portion of a circuit within an established period of time when a current to ground exceeds the value established for the device. So what happens during a ground fault? Now you get this high voltage flowing into this low voltage, and if the power's on during that time and you always have that supply of high voltage, then it's like a waterfall of current that's falling out of the wire as quickly as it can into ground, and it gets so much current that it could heat up and start a fire. And so we have a ground fault circuit interrupter that can detect when a ground fault is occurring and then lift the breaker up in the service panel, de-energize the equipment, and you know, interrupt the ground fault. Then we have an arc fault current interrupter, which is a device intended to provide protection from the effects of arc faults by recognizing yada yada. Arc faults are different than ground faults. Ground faults are when the electricity goes from that ungrounded conductor, that high voltage conductor, and it touches a low voltage component, like a metal part that has no voltage on it, and it's connected to the equipment ground conductor, and the power spills over into the EGG and flips the breaker on your panel. Arc faults are different. Arc faults are like if you imagine you take a power plug, and I do not, you know, don't do this, just imagine it. Let's say you have an extension cable connecting a generator to a load, and you're daisy chaining extension cables together, one after the other, and you take that extension cable and you under load, you try and pull it apart. You know, then that's very dangerous, but in the cartoon version, you might imagine this arc of electricity going between the male and female lead as you try and pull it apart. In a solar array, where that kind of fault might occur is in the module-to-module connectors. You know, what they're called are MC4 connectors. So these are MC4 connectors, and they form the module-to-module connection. And then at the end of a circuit, you build a custom MC4 connector, and you run it all the way back to where your inverter is. And usually the module-to-module MC4 connectors are of high quality and compatible. But the problem is, even though a variety of MC4 manufacturers make these MC4 connectors, when you go from module to module, it's the same manufacturer providing the MC4 connector of both sides. But when you get out into the field, you source your MC4 connectors from a third party, and there's quality differences. And so while they all are standard and match up together, there is a quality difference between high MC4 connectors and low MC4 connectors. And it's not just a manufacturer quality, it's a workmanship quality of how well, you know, let me clear my mess here. You know, you run a conductor through the end of this and into this metal housing, and then you crimp the housing, and you have to snap it into this conductor, and then this piece twists and kind of rotates, and you have to make it up tight, otherwise it doesn't connect the cable to the pin. And so there's when you're making up the MC4 connector in the field, there's a number of spots that can go wrong. And lo and behold, my experience is it's the MC4 connector that is the most common point of failure. And so you have a poorly made up MC4 connector, and rather than connect to ground, it's just you have a positive and negative side of your cable, and every so often either current doesn't flow or you get electricity arcing and still flowing, but that can produce heat and smolder a cable and start a fire, and that's obviously dangerous. And so National Electric Code over time has, it used to be that it just required ground fault protection and ground fault circuit interrupters. Nowadays, the inverters have arc fault detection in them as well. And that's produced kind of a phenomenon where owners of older systems think that solar arrays are bulletproof and nothing ever goes wrong with them, whereas you install a newer inverter with the arc fault detection and it recognizes when that MC4 connector is not made up correctly but still operational, and it shuts off. So that's for the best, but it's also showing you that older legacy components, eventually should be upgraded to the latest iteration of code. In fact, in your old school central inverters, the way that their ground fault detection circuit was intentionally grounded, it's called a grounded inverter. And it really has to do with the ground fault detection and how the DC side ground fault detection detects ground faults. Does it reference a voltage to ground, or does it monitor that voltage in a different manner? Is it a grounded or an ungrounded inverter? And in grounded inverters, when you have multiple strings, there's a blind spot in the old school central grounded inverters on commercial systems that has burned a couple buildings to the ground. I guess that's a bad pun. So anyway, there's ways that we can reduce these ground faults. For ground faulting, generally you don't want to make your circuits unnecessarily long. To reduce ground faults, anywhere where your circuits can be dragging across a hard surface or against a surface that has a jagged edge on it, such as where a conductor meets, or a conduit meets another conduit, all of that could expansion fittings that don't work, can cause a problem. If you keep your array subsections small enough such that thermal coefficient of expansion is no longer necessary, then you get less of a need for expansion fittings. There's fire code that says on commercial buildings every 150 feet you got to put a walkway for fireman access. And then you think, well, if I'm using a forced ventilation system, do I need to do that? Well, there's other reasons why rooftop clearance requirements on your solar array are worthwhile. It's not just about fireman safety, but having smaller subarray sections reduces thermal expansion. On top of that, your wind loading. You get, if you stay off the edges of your rooftop, your solar array has less wind loading. And so structurally, it's better to stick to the interior of your roof. Arc faulting, it's more about, are your connectors made up tight and correctly? and then avoiding fine strand conductors, but you don't use fine strand. You use stranded conductors in solar, but it's not fine stranded. Article 225, outside branch circuits and feeders, wiring on buildings. The install of outside wiring on surfaces of buildings shall be permitted for circuits under 600 volts nominal. And let's see. And then it lists out different ways that that you can have wiring on buildings. So you think, well, can I just go and staple a wire to the edge of the building? Code has a list of ways you can do it. You can have wire in metal conduit, wire in PVC conduit, wire in cable trays, and even certain cables that we'll get into in section 300 have protection and support built into them. And so if you see just a random cable running up the edge of a building, either it's the system ground, or it's a special cable that probably has a harder shell around the exterior of it. Outside branch circuits, where outside branch and feeder circuits leave or enter a building, there are some restrictions that are further on down into code. Support spacings. This 225.12 will govern what the distance is between straps, what the distance is between putting little neoprene support blocks or rubber pad support blocks underneath your conduit as you run across a flat roof. As you go up the rooftop, because of the weight of the cable that is just hanging in the conduit. And where does that weight go? Well, it goes into the conduit. And so every so often you need to strap that conduit onto the wall and transfer your load, into the wall, the support wall of the building. All of these things are picked up in code. Well, for that matter, the solar design software only goes so far. The furthest that I see solar design software going into the industry is what we just saw, where it gets into conduit sizing and conductor sizing. But I don't see any industry software going all the way into calculating all the straps and all the rubber support blocks that you need. And so if you're unfamiliar with code, this is this is where like the scope handoff would occur between, the designer and the general contractor. The designer and the installer who's pulling the permit and performing presumably a design review. Supports over buildings, attachments to buildings using masts as support, clearance for overhead conductors and cables, and there's different scenarios for going from 10 feet up to 18 feet of clearance requirements. This is where, going back a few slides into the the crow's nest, or the weatherhead on, well, how tall up does this weatherhead need to be for these power lines from the utility to just drop down and be taped up? And these are overhead wires. So how tall up does this need to be? Well, right hidden in the very beginnings of code, where we're still talking about feeder circuits supplying power to a service panel, that's where that is. Often it'll be a 18-foot clearance. Clearances from buildings for conductors not over 600 volts, above rooftops, 8 feet above the roof, or not less than 3 feet away from the roof in all directions, except when the roof is subject to pedestrian traffic. So if there's a rooftop deck, if you have a overhead power line going across your rooftop deck, that may need to be 18 feet high instead of 8 feet high. The final span, eventually these wires have to go into the building. So the final span between your wires in the building should be 3 feet away from windows and doors and porches and balconies and ladders. If you have someone who's going to hang 3 feet out a window and grab onto a power line, not much you can do in that situation. But then again, if your power line is, you have a 3-story tall row home and your power lines just go up to the top of the home, uh, you're running your service conductors from the power line to the house. It's only on that top span at the very top of the unit where you can get closer to the window to stay just on the top edge of presumably an inaccessible rooftop. So the final span, you have to stay 3 feet away from your windows and porches and balconies and ladders, unless you're at the top level of the home, at which point you can just go above the window, between the window and the top of the building wall. And then conductors on buildings, structures, or poles require mechanical protection, subject to requirements that we still have to get to. Multi-conductor cables on exterior surfaces have different requirements. Raceways, the main thing about raceways on the exterior of buildings is that they need to be arranged to drain and be suitable for use in wet conditions. So in other words, you might have your wires coming out of your array into a box or into the roof itself. You might be going from a box into the roof. Well, you don't want to arrange your wires and conduit such that, let's say you put the box at the bottom of the rooftop instead of the top of the roof. If your entry point is at the bottom of the rooftop, it could be that the water is flowing down the roof and then it might run into the box. And I've seen this before on actually, it was on Half Moon's rooftop. We put a pipe boot on a large piece of conduit and ran it into a PVC box. And there are a few things that did not get done on that box. And what happened in this case was, it was the combination of a heavy rain is when they noticed the water coming into the rooftop. And the contractor had not sealed the inside of the conduit. And so what happened was the water was pouring down into the box and actually getting up into the box. The fault was that while the pipe was in a pipe boot, the contractor did not put additional sealant between the pipe boot and the fitting inside the box. So water was getting into the box and then falling through the conduit into the attic. That was not arranged to drain. If we had instead taken that box and located it up to the top of the rooftop, you wouldn't get the water running down the edges of the conduit into the internals. So you have to think about drainage, and then again we've talked about raceway seals as well. Where a raceway enters a building or structure from underground, it should be sealed. Spare or unused raceways should be sealed. Sealants should be identified to use for use. So you have to use listed sealants. You can buy these things at your local hardware store. Then we get into the number of supplies. So a building or structure that is served by branch circuits or feeders on the load side of a service disconnect mean shall be supplied by only one feeder or branch circuit, unless there are special conditions or special occupancies where the space constraints make it untenable. And so this is kind of interesting. It's referred to as the 6-handle rule. It says a building or structure served by a feeder circuit on the load side of a service disconnecting means shall be supplied by only one feeder or branch circuit, unless you have a separate power system for fire pumps or emergency systems, or you have on-site power resources like solar or generators or standby. So what that says is you should not have two utility services feeding the same building for no reason. Just because you want power on that side of the building and the other side of the building. The building has to have the one supply unless there's a special reason or special condition for it to have two. Then again, supplies only go up to be so powerful, and so you're allowed to add additional supplies to a building when you're at a supply voltage of 600 volts or less in excess of 2000 amps. So let's say you're a commercial array building and you're on a 480 volt service and you have 2000 amps of service. That's around 10 to 15 megawatts of power. And if you are an on-site manufacturer and you need even more power than that, once you get up into those higher levels, they give you the ability to get special permission to have multiple services feeding the same, building. Disconnecting means shall be provided for disconnecting all ungrounded conductors that supply or pass through a building or structure. And so if you are penetrating through a building between your generator and your battery bank, or your generator and your service wall, or your solar array and then into your building, there needs to be a disconnect. And in the past, this disconnect requirement has been very confusing because there's also the utility disconnect, which really, when it boils down to it, it says it can be located outside the building or inside at the first available spot. Really what utilities want is they want a disconnect on the side of the building that they can use to turn off your on-site power systems. And maybe that'll be multiple disconnects for when you get into having a solar array and a electric charging vehicle station, something like that. Does there need to be a disconnect up on the rooftop? It says you need to have disconnecting means for disconnecting all ungrounded conductors that supply or pass through a building or structure. And actually, we get into rapid shutdown, and what we realize is that in the past, we've just taken the conductors from the array and fed them directly into the string inverter, and installers have been kind of getting around the spirit of this by staying outside the building, and they're not passing through the building. But as installers get more experience, they say, well, I want to keep the conductors inside the building for a few reasons. If it's inside the building, A, it looks good. And to sell residential arrays, you got to make it look good to be in the business over the long-term values is what we're talking about. When you're inside the array, it's not exposed to the weather. You get some really mean squirrels out there that can, So when you go into the roof, there's actually a box up on the rooftop that doesn't always disconnect, but can disconnect. It's part of your rapid shutdown system. Location. The disconnect shall be installed either inside or outside the building where the conductors pass through the building. The disconnecting means shall be at a readily accessible location nearest the point of entrance of the conductors. For the purposes of this section, the requirements in 230.6 shall be utilized. Well, now we have some new definitions to talk about. The first is what is accessible, and then what is readily accessible. So accessible is that the device can be easily approached. Readily accessible is a little bit different. It's being quickly approached. And the spirit of readily accessible is essentially without requiring people to grab a tool. So to grab a ladder or something like that to get access to that disconnect, so you don't have to climb over obstacles. And so accessible means that you can get to it, but readily accessible means you cannot use any tools other than perhaps a key to open up the accessible device. So something that is permanently enclosed into the building facade would not be considered accessible. And then there's also a definition of in sight from, which is typically where you can see it from point A to point B, and it's not greater than 50 feet. Definition of disconnecting means shall be provided for disconnecting all ungrounded conductors that supply or pass through a building or structure. So the question is, does your disconnect need to disconnect the neutral? The answer is no. In fact, sometimes you should not disconnect the neutral. For instance, if you want to have a autonomous relay, an automatic relay between your utility and your transfer switch and your on-site generator and your solar array and your battery bank, where you want when the power goes out, you want the switch to flip and you want to go on to your battery bank, and then you want the generator to turn on when your batteries deplete, but then when the power comes back on, you want to switch back on to grid power, and you want it all to happen automatically. Well, you may need to have a neutral be fully connected throughout the entire system in order for that kind of automation to occur, so that you can monitor the status of the grid versus the status of your generator versus the status of your battery bank. The disconnecting means shall be at a readily accessible location at the nearest point of entrance to the conductors. Well, is a rooftop readily accessible? No, you need a ladder to get up onto it. And so what we're talking about for this disconnecting means is really, the utility is looking at that knife switch disconnect on the edge of the building as the system disconnect, or the main solar array disconnect. The disconnect up on your rooftop in your rapid shutdown, that's considered an additional disconnect. And so the readily accessible requirement doesn't apply for whatever reason. Finally, we get to another disconnect rule, the maximum number of disconnects. This is known as the 6-handle rule. And it says the disconnecting means for each supply permitted by 225.30 shall consist of not more than 6 switches or 6 circuit breakers mounted in a single enclosure. Well, what does that mean? Well, we know what an enclosure of switches are. It's our electric service panel. And so what it says is, here's an electric service panel, and it has 6 switches on it, and it's being fed by a supply, and let's say that's our supply coming in from the top. The disconnecting means for each supply shall consist of not more than 6 switches. And so what that says is, if I have and this the reason why I'm having trouble explaining this rule is because let me approach it from a solar design perspective. Let's say I have, let's just go back to our half moon array. So on our half moon array, we had 4 solar panels coming in. And so solar panel 1 lands here, solar array 2 lands here, solar array here, 3, solar array here, number 4. So am I allowed to put all of these supplies onto this one panel and then connect it to the grid? The answer is yes. I can do up to 6 switches on a single supply. Now, what happens if I have 7 inverters or microinverter branch circuits or what have you onto this panel. And so now I no longer have 6 switches, I have 7 switches. Well, at that point, you put in a main breaker, and that becomes your single switch disconnect switch. Or alternately, you put in a knife switch disconnect with a fuse, and that would serve in lieu of the main breaker. But in either case, you have your main overcurrent protection device and switch where you can flick no more than 6 switches to fully de-energize that supply. So then we get to the grouping of the disconnects, and this is one that stuck out at me. Each disconnect should be marked, and then they need to be grouped. So those 6 disconnect switches, whether it's 6 breakers on a panel or 6 individual knife switches with their individual fuses, they have to be grouped together in the same location. And so you can't just have 3 microinverter circuits on a panel and 3 microinverter circuits on a panel on the other side of the building, both coming in to lugging on to the utility meter inside the main service panel. They would have to be on their individual disconnect switches right by the main service panel, no more than 6 of them. Okay, well then there are reasons for additional disconnecting means, and that would be for your emergency backup systems or even your standby systems. And so here's the problem. Let's say the fire department shows up and they want to power down the building before they go inside. They should not have to flick more than 6 switches to de-energize the building. And so they get there and they flick all the switches. Well, what if one of those switches powers the respirators? And so by flicking that switch, the hospital loses its emergency backup power, and all of a sudden their patients undergo cardiac arrest or whatever. And so standby switches and remote and emergency switches should be located remotely from the disconnect means for the normal supply. But then again, at the residential level, if the house is on fire, the fire department shows up, they don't want to turn the building off only to trigger the emergency power system. And usually with a generator, it's very obvious to the firemen that there's a generator on site. They can just run over to the generator and turn off the generator disconnect as well. But what that means is when you get to where's the disconnect on your battery system, on a grid connected battery, is that disconnect going to be located remotely, or is it going to be located right next to all the other services? I think we're really splitting hairs here. As long as you have no more than 6 switches grouped in one location, and it's all related to power supply, you're going to be fine. If you have a standby system where it doesn't really matter if it gets turned off or not, you don't need to worry about it too much either. But if you're designing an emergency backup system where there are critical loads that must remain energized, even when the fire department is trying to purposefully power down the building, those switches need to be separate from the normal power supply to indicate to the fire department that they're there. Now, also, those switches need to be grouped in the same location. And so what that means is you can actually have 6 normal grid-connected solar power switches, or your utility main, and 5 line-side connected solar arrays as well, all grouped together. And then you can have 6 additional switches for various battery banks on the outside of the building, for various battery banks and generators for your backup power systems. Uh, Identification. So where a building or structure has any combination of feeders, a permanent plaque or directory should be installed at each disconnect location, denoting all other service feeders supplying or passing through the building, with exceptions for multiple connected dwelling units or industrial buildings. Um, and so what that means is when do you have a combination of feeders? Well, we learned that feeder circuits are your utility service, and also feeder circuits are your solar array circuits. So whenever you have circuits from your solar array and circuits from your feeders, a plaque should be installed denoting that there are multiple feeders on the job site. Um, and you may even need to have a map of that location, depending, not just a call out, depending on the voltage of the system. So what can these disconnects look like? You know, when I go and I to the solar conferences and I look at battery inverters, the battery inverter companies are very pleased to show off their motorized breaker switches. The answer is, well, what do you need a motorized breaker for? And at first glance, it seems kind of neat, because if you need to disconnect something for some reason, let's say you have a battery bank and you want to turn your air conditioner off so that you avoid some peak load. You know, you could press a button and motorize that breaker to disconnect your air conditioner, and then when you're out of that peak time, you can press the button and close the breaker again. And those motorized breakers right now cost about 120 to 130 bucks. But the rules on those motorized breakers, if they're going to qualify as the disconnect, they also have to be hand operable. So sometimes the little tab will stick through the motor and you can wiggle the tab back and forth by hand, but the motor will still also separately operate the breaker. Otherwise, they need to be separate. The disconnects need to operate both poles, both positive and negative poles. Um, they can have the means to disconnect the neutral, the grounded conductor. They need to indicate if they're open or closed. And then there's some minimum ratings of what's the smallest disconnect size requirements. And this one's interesting. On a single circuit, you got 15 amps. Single family home, there's a minimum 100 amp mandate. So you can design a house and only specify a 100 amp service panel if you want to. You know, assuming that the other parts of code that we talked about before are met, you know, square footage being one of them, or you do a calculated load test. And then we get to the all others of 60 amps. And what we'll see later on is that for supply side connections, they're really looking for a 60 amp connection on supply side. You know, as far as the minimum cable gauge and rating for that supply side connection. Not that you know, you can have a 60 amp rated main breaker and a 60 amp rated cable and then plug in a 20 amp microinverter. But most of those supply side connection taps on the market are for heavier gauge cable that is associated with 60 amp service. Up further than that. The special rules for 600 volts, including additional clearances for roadways, rail lines, water, you know, for additional disconnects. You know, we have 225.52. We have electrically operated disconnecting means, additional requirements, including a indicating switch on the directory plaque. You know, sometimes like the requirements from the knife switch disconnect at the residential level, that knife switch disconnect is not part of code, but often the inspectors are treating your residential arrays kind of like distributed power systems, and they're used to seeing knife switches on distribution stations and substations, and so they like to see them on your solar array as well. Um Let's see. So substations have a warning sign that says each operated isolating switch or disconnecting means shall bear a warning notice to the effect that contacts on either side of the device might be energized. A permanent, legible, single line diagram of the station switching arrangement, clearly identifying each point of connection to the high voltage section, shall be provided in a conspicuous location within sight of each point of connection. So on a substation, wherever you connect to high voltage, you have to provide a permanent placard of a single line diagram showing that switching arrangement. And when you get into, say, commercial design, and you might think, well, what are all the signage requirements that I'm going to have to get into? Here you see a call out that says, well, for substations, which are higher voltage systems, I need to have a plaque with a single line diagram identifying the points of interconnection. And, when you get into, it's not uncommon on commercial inverters that are going from the 600 volts of the array into the 480 voltage of the utility primary to put a single line diagram around the inverters as well. So what I'm saying is, if you're thumbing through code and you look at just a general section that says services, and it says you have to put a single line diagram placard here if it's over 600 volts, such as at a higher voltage substation, you might find that when you get into the 1,000-volt section of the inverter equipment down in section 690 or past that, that they have similar requirements. Number of services. A building or structure shall be supplied by only one service except for these special conditions. I think I'm kind of repeating slides here. Conductors, one building or other structure not supplied through the interior of another. So if I have a row home, I'm not allowed to take the power lines from outside the building and then put them through the floor of another building and then tie those into a third building on the other side. Unless there's special conditions like I'm burying them in concrete or putting them in a concrete raceway, or there's a vault, that's just a concrete barrier around where the cables are going under. So essentially it's saying, hey, the cables need to be connected if they're going, or protected and heavily protected if they're going from unit to unit. Basically, they have to be encased in concrete. Okay, so then we have other conductors in the same raceway or cable are not allowed except for grounding conductors, bonding jumpers, and load management control conductors with overcurrent protection. And then we get another raceway seal call out that says, you have to seal your raceways. And we've already seen those scenarios when we were talking about feeders, and they're the same for services, which are a specific type of feeder and therefore coming after the feeder section. The requirements are pretty much the same, but feeders and services cannot share conductors with load devices. Same clearance requirements. Insulation. So service lateral conductors shall be insulated, except a grounded conductor shall be permitted to be uninsulated if it's bare copper in a raceway, or bare copper for direct burial, or bare copper where part of a identified cable. So without getting into that, there's sometimes you'll be using bare copper on a job site, but otherwise, like your neutral wire needs to be insulated. That would be a grounded conductor that has insulation on it. We have services, a call out being not smaller than number 8. Then we get a protection from damage where entering a building, they need to be protected in a raceway. Spliced conductors. So you know, there's the grounding system that needs to be permanently spliced. And so when you're running your copper wire, your bare copper wire up to the rooftop to land on the solar arrays and ground it, you may want to run another section of ground off to another subarray. And the only way to take two pieces of copper and put them together and consider them to be permanently connected is to take a crimping tool that is hard as heck to use because it's so large. You know, number 6 and number 8 copper are pretty thick, and you put a crimp around the two pieces of bare copper, and then you press this thing together as hard as you can and permanently crimp them together. It's not nearly as good as using a continuous run of copper, but it's considered to be continuous. You know, putting an acorn to connect your bare copper to your ground rod, you know, will require protection. So, you know, conductors need to be protected. Service conductors are permitted to be spliced and tapped, but only under certain conditions. So if you're inside an electrical box for a supply side tap, you are allowed to tap onto your service conductors. And how many service conductor sets can you have going into a building? You know, as long as they are grouped together. If you have a special need to have more than one set of service entrance conductors, such as buildings with more than one occupancy, you can have 2 to 6 disconnecting means grouped together in one location from one service drop. All right, so for service conductors, you know, their sizing based on 125% of continuous loads plus 100% of non-continuous loads. And then it says grounded conductors not connected to overcurrent devices shall be permitted to be sized at 100% of the total load. And so what that's saying right there is that the neutral wire, if it's not connected to an overcurrent device, is permitted to be sized at 100% of the load with no additional 25% allowance for the continuous load. And what that means is there are situations where the neutral line can be undersized, and it might save the client a little bit of money. However, in solar, you're generally not undersizing the neutral just to avoid any mistake for the time being. All right, so let's see where we're at here on time. To kind of finish out section 230 before the end of class, just give me a moment here. Where did my presentation go? We have the neutral conductor shall be, the size of it is governed by a particular table in National Electric Code. Where an AC system under 1,000 volts is grounded, the neutral is routed with the ungrounded conductors to each service disconnect. So your neutral is going to be running throughout the system. Now let's look at this wire diagram here. Now we have our, let me get my laser pointer out. We have our grounded module frame going onto a ground bar. So this might be inside a PVC box. So instead of the ground rod going on from the metal frame to the rack to the box frame, we're just making the ground inside this ground rod. And then that's carrying the equipment ground to the metal inverter box. And then this is also going, maybe that's a permanent crimp, but it's also being connected to the ground bus on your main service panel. So we see a fully interconnected grounding system, and there's special rules on what constitutes as a grounded system. So often with solar arrays, you actually need two grounding electrodes rather than one grounding electrode, particularly when you're using ground rods. And so we see two grounding electrodes here. Actually, they're using it in the form of a ground ring. We're going to talk about that in a minute. And then we see this, there's no neutral wire in the solar array. It's a DC system with a positive and a negative. But in that combiner box, nowadays, it's not uncommon to run a neutral wire up to the rooftop anyway. The neutral wire is at that point used as a signal between the rapid shutdown box and the inverter. So when the inverter detects a grid failure, it'll send a signal through the otherwise unused neutral wire up to the rooftop where the combiner box is. Then we trace back this neutral, and maybe there's a transformer inside the inverter or not. You know, if there is, regardless, we're sharing the neutral with the utility neutral. And then finally, right here inside, and look at this very carefully. This circle right here is where the utility meter plugs in. So this is a integrated meter load center combination box. But sometimes this, and more commonly, I guess, the meter and this point of attachment is in the utility meter box, and the load center is your service panel that's inside your garage. And so inside the meter can and meter base, this is where we had that question from earlier. Where is this neutral connected to ground? And the neutral is connected to ground at one point, and that's inside the utility main disconnect. And see, we see this connection, this bond between neutral and ground.